So finding a solution here for the first example, sort of trivial because it's a linear equation system and not a problem using any technique known to us solving equation systems. Now include velocities. We don't have any pressure yet. Well, maybe he's disguised inside here. We don't know. But now we have a velocity. And again, you see now it's a sort of a linear way of cheating because, of course, the generic unknown phi is going to be a velocity in the end, either u or v, depending on which component of the Navier-Stokes we are looking at. But we treat these velocities as sort of something else. So these terms are linearized. Cheating. Very bad, but we sort of have no choice. Actually, we do, but never mind. So what will the unstructured mesh systems now look like? The right-hand side we have sort of dealt with already. That's the elliptical equation for you. Not a problem with him. So the question is the convective terms to the left. How to deal with those? Well, actually, it's rather straightforward. So we're going to need here now a flux of a velocity, v vector, multiplied with the transport of, sort of being a transport of our unknown phi. That will now also be a flux term, a convective flux term. And we use the same interpolation schemes. Here, treating the velocities as something known. They are sort of given. Then, due to the linearization, they should be unknown. So what do we do here to linearize? Maybe we use the velocities from the previous iteration, previous time step, something like that. But to call them unknown, then we are in trouble. Then we have a nonlinear equation system, hard to solve. Here again, we also say for the triangular mesh system that everything is stored in the corners, also the velocities. So then we can create an average velocity for covering one single triangle, just a simple average like this. And then we have the velocity vector sort of should cover the entire triangle. And covering the triangle, not so stupid if you think in terms of what we are seeking. Better draw it here. So that was 1, that was 2, and number 3. Center point, midpoint. That was A, O, C. So we are going to do a line integral from A to O and from O to C, covering all fluxes. And now if we have one velocity covering the entire triangle and it's been calculated sort of around this midpoint in the triangle, then he should be a very good representative for the velocity for these two line integrals. At least not so bad. You might want to improve it if you look at the next triangle as well. Midpoint here, like that. So maybe creating one average here, another one for the next triangle. Then you could start some interpolation tricks here if you wanted to try to improve the accuracy for covering the flux, the advective flux from this term. That could be done, but it's actually not worth the effort, to be honest. We are going to do so much cheating anyway, so a little bit error here and there, not a big deal. So here they play around with flipping the equation system so that you actually introduce the local cell Reynolds number, the local Peclet number, into your equation system. That is a neat trick just to keep things stable. So one way to do it, not actually necessary, but instead of here you see, instead of x, we now have this direction xc. Of course it is an x direction, but it's just assure you don't go too far. Remember for one single triangle you have the average velocity here, say in this direction, v vector average, and then you created your coordinate system something like this. That was the big y direction, and up here was the big x direction. And then you now say my x shouldn't be longer than so and so to keep things stable, and also to keep the cell Reynolds number under control. So you sort of have included some stability criteria, Courant number, Peclet number, into the scheme. Of course, an option. The rest of the discretization, sort of rather straightforward actually. You do the same as we did the last time, only now we have a couple of additional terms. But you will end up with sort of the same equation system. We don't have to go through all the details here. So in the end, you will sort of have the same recipe as we had the last time. Then we had C1, C2, C3. Now we have D1 to D3. And the different Ds then hopefully should be independent of our unknowns. And indeed they should be. And they are listed down in the appendix. So you can have a peek if you want to see how they look. So you might say, on an exam, on a possible question with this, I won't go into the detail here with unstructured mesh systems, including the velocities. I'm not too fond of the way they've done it, so skip the details here, unless you are interested. You have the recipe given, you have all coefficients needed to write your own program if you like, so everything is here. But a little bit too tedious in my point. So if you have understood the first part, the elliptic part, then you also will understand this part. That you'll see if you look at some of the old exams. Have I put some old exams out for you? Have I forgotten that? Yes. Too bad. I'll put out some old exams and you can have a look. So again, you get the algebraic equation system, and okay, boundary nodes have to do special. So not a problem there. So all the else is actually straightforward. It doesn't include anything else, except of course some numerical noise, as you are aware, with stability. So we have to pay a little care with our choice of delta t, or even the choice of delta x, delta y, meaning the size of these triangles, that they must be small enough to cover, to ensure a local Peclet number smaller than, and so on. So it's stable. Now looking into the entire Navier-Stokes. That is a little bit more tricky. So when this was written, they didn't really like this problem that we had with co-located mesh. If you can recall from the Sola algorithm, the sort of first obvious choice was to put the velocities and the pressure in the same point, co-located mesh. If you did that, you will you will get into trouble, because in the equation here, when you then have to calculate the pressure gradient, derivative of the pressure, typically what you will use is the pressure to the left and to the right, or to the top and to the bottom. You don't use the center point itself. That doesn't enter into the equation. So then you risk creating pressure fields where every, sort of in a checkerboard pattern, every white pressure will have one solution, and the black pressure then will then have a totally different solution, and they don't talk to each other. So it could be rather messy, rather tricky. So to avoid it in Solar, we use staggered mesh. Nowadays, they have tricks to remedy this, so a little bit messy. I won't go into that details, but it has turned out that the co-located mesh again has been very popular. When this was written, they still said, dangerous, difficult. We have to stagger the mesh or do something to avoid it. Yeah, here they have even added a general conservative equation. Could be anything, energy, concentration, whatever. So how to solve this one? Well, they split it up into macro elements and sub-elements. So they sort of do it like this. If you start creating a fine mesh, then very easy to split up every triangle into 4 triangles, creating an even finer mesh. So for one triangle, as you can see, straightforward then when you have the midpoints here to create 4 triangles. So you go to an even finer mesh, and then you solve for some of them. For the fine mesh, you will solve everything, and on the coarse mesh, you will only use the pressure. So here you see it. For the coarse mesh system, the open squares, that is the pressure. So the triangle to the left there, only 1, 2, and 3, they will be pressure and velocities. But on the sub-mesh level, 4, 5, and 6, there we have also velocities. Not pressure, only the velocities. So this is one way to do it, one way to work around this staggering pressure system. Quite possible. But it means to cover the physics, then the pressure will suffer from not so fine resolution as the velocities, of course. But for many problems, this will work quite nicely. So the pressure changes in a flow might not be that huge. Remember, in a boundary layer here, you have a strong velocity gradient. Yes, we have. But the pressure gradient inside a boundary layer, constant pressure. So the pressure doesn't change much, even though even perpendicular to a wall. But the velocity does a lot. So it's not a bad philosophy. Resolve the velocity nicely, but we don't care too much about the pressure. So that's okay, it works. So that's a good philosophy. It's a sound philosophy. Yeah, the rest is actually just repeat as the last time. No changes. You have to deal with the pressure, of course, somehow. So you will have some additional pressure term. But else everything will be the same. You have to define, of course, the variation, and again, only linear variation. Also here for the pressure. So you will have a new set of coefficients that has to be calculated. And here, now you are on the coarse mesh. Nothing to do here with multigrid by all means. So we only have a 2-mesh system. Pressure only in the big triangles in the corners there, but the velocities, they will also be on the fine mesh. And you end up with the same discrete equation system, with one exception. You will now have, don't have to go to the details here. We will have equation systems that sort of couples unknowns, velocities, and pressure. We have one unknown too many. So that is here a problem, how to calculate it, how to find the solution when we have coupled velocity and pressure in the same equation. Sadly, there don't exist any equations saying time derivative of pressure equals something. That would be very nice, but we don't have it. So again, the same problem that we had with the Sula algorithm, the projection method, how to update the pressure. Well, you have no choice. Somewhere along the line, you have to use the continuity equation, of course. So here they're using something called a simple C, but I'll go through the classical simple for you, so you can see a little bit easier to see the details here, sort of drown in all these different coefficients. But you can have a peek of these systems for yourself if you want. So you have to set up an iterative solution algorithm. Simple, you have many of these simple versions. So here's a simple C. And you have simplex, simpler, simplest. I have a bunch of them. Before we do that, we can have a peek into the other one. What was that one? Number 2. So it's just another way of order or defining your mesh system. So it's still the full 2D Navier-Stokes, but a little bit different way of thinking. But in practice, you'll end up with the same equation system. Not much difference. Little discussion when you are going to 3D, but it is more or less straightforward. Although, might be worth mentioning, when you go to 3D, what you try to avoid, if you have very complex geometry, is to start using pyramids as elements. Pyramids, they can of course model any complex geometry in all dimensions, but they will become quite inefficient. Way too much bookkeeping. So the way you want to do it, preferably, say you have a complex geometry in only 2 dimensions, but you need to calculate the full 3D. Then you just extract your unstructured mesh 2D into in the last direction. So your cells will not be pyramids. They will be something like this. So you just push them further in in the last direction. Much better, much more efficient. So totally unstructured in all 3 dimensions, that's messy. A lot of bookkeeping as well. Possible, and on a modern software, you just have a button saying unstructured mesh, so you don't care about it, but it will typically be quite inefficient. So try to avoid it. But else, it's actually straightforward. And I think in the end here you should have the appendix. Then giving you the entire setup for the coefficients, for the constants. So here you see the problem, the variation of your unknown here based on A, B, and C, which are not constants. They are very they are dependent on the solution itself. So no, we don't like it like that. Of course, you need that one in the end if you want to plot it, but then you know the solution, so then it's not a problem. But during the calculations, we want to be based on coefficients independent of the solution, only dependent of the geometry. So much, much better. So this, a little bit careful here, because the velocities is going to enter into the coefficients. So not totally independent, but pretty close. Some of them will be independent of the solution. So yeah, but I won't go into the details. It's not worth it. Any questions to this control volume finite element based method? It's okay? Then let us see here. Ah, actually worked. They never have a mute button on this primitive. Let's try to cheat. Don't we have a screensaver or something here? No. Display. Can anybody see any screensaver? No. No, not there. Power and sleep. No, never mind. Normally I use a screensaver and then I just say use black. So now I'm going to go through how to solve this coupled algebraic equation system, and it's called semi-implicit method for pressure linked equations. And it then reads out to be simple. So that's the idea. So I just write one component from the Navier-Stokes. Time derivative, rho u, x derivative, rho u square, y derivative, rho u v equals, and then we'll have the pressure gradient, the pdx, gravity I'll skip, and then mu double derivative. There we have it. And from that equation, integrated, discretized, you will end up with an equation system then looking something like this. For the center point P, you have a coefficient A for the unknown velocity. That's point P, that's the one we want, equals then the sum of the neighbor coefficients and the neighbor unknowns, like that. And then we will here have something, depending on how we do it, multiplied with a pressure difference. And there also is a staggered mesh. What pressure differences will be changing depending on your method. But anyway, it will include the pressure somehow, and then we will have maybe an additional constant. So that is the starting point. Need some more color. Say initially we have a velocity field from the previous time step or whatever. So we will now say the pressure, this guy, that is unknown. I don't know him. But for closing this equation system, we have to put something in there. So I now guess an initial pressure. You construct it or take it from the previous iteration or something. We use a pressure P star, I think it was. Yep. We guess that one. Then, after finding a solution here, we will then obviously have to use a better pressure. So we are going to need some corrections. Correct pressure. We have to adjust it. So then we say the right pressure, that is P. That's the one we are seeking. That's the one we want. He will now be equal to the one we guessed plus a pressure correction. Pressure correction. Pressure correction. And then we are now actually seeking an equation involving the pressure correction. How can we find the correct adjustment needed to update him to be right? And of course, you do the same now with the velocities, because using something wrong up here, solving this equation system, you're going to find a velocity which then is wrong. So you can do the same here as well, and in both directions, like that. So you have pressure corrections and you will have the velocity corrections as well. So the first equation, the one that we really wanted, then you have the sort of the correct new velocity based on the correct pressure, which we don't have. So that's sort of impossible. So we have to sort of admit that we can at the most find this tentative velocity, as we called it in the projection method with Sola. So the actual equation system that we can solve will look something like this. U neighbor star, and then something delta P, and then this guessed pressure plus B. So here, if this is equation number 1, this one equation number 2, then we subtract them, 1 minus 2, and what do you get? Well, you get the correct one minus this tentative, which is just the correction. That's nice. So here you will get a P u correct when you subtract these two. That was the left-hand side. And same goes with actually all the neighbors. So here you'll now have sum of all the neighbor coefficients multiplied with the neighbor velocity corrections. And for the pressure, yes, we will have the same there as well. Something involving the pressure correction. The constant B disappears. He has been removed when you do the subtraction. Not a problem there. So still doesn't help. This is one equation with two unknowns. You of course have the same equation with in the y direction with the v velocity. And then we do something very, very bad. We say this one is 0. Hey, what's this? That's definitely not 0. So when we write up here initially, we write semi. Yes, it's very semi indeed. So that is one dirty trick that we are going to do. And then we look at the equation that we had here for the velocity. And now that one can sort of be rewritten. U at the point P, the correct one, well, that was equal the first one that we could calculate. And now we substitute the unknown velocity correction with the pressure correction using this equation here. You see, you just substitute u fluct with this guy. So he will read something like this. It will be 1 over a p pressure fluct, and then maybe something else as well, depending on how you have discretized the original equation system. Still doesn't help. Still one equation with two unknowns. But now, finally, we use continuity. Of course, you have to use the continuity equation, since we are missing one unknown. Continuity. Continuity equation, he should read something like this. In general, time derivative of the density, and then you'll have x derivative rho u, y derivative rho v equal to 0 in 2D. So then you take the one we find here from this one and insert here. And then of course you do the same with this one for the other direction. But then you sort of substitute away these velocities here. Then this one, this equation, is going to end up to be one equation for the pressure correction. Equation for pressure fluct based from continuity. So that is the trick. And now the simple algorithm. You can calculate this tentative velocity field, the first one, by using something crazy. You guess an initial pressure or use it from the previous time step or whatever. You find a velocity field that then in general will not be correct. Next, you then solve the continuity equation, actually now for the pressure correction. And then update, finding the new pressure. And when you have found the new pressure, then finally we can go into our original equation system, adjusting for the velocities as well. So that is, this is the classical simple method. And it turns out if we sort of do this on a uniform mesh, constant delta x, delta y, you will see that this method is identical to the projection method. It is exactly the same. So, of course, here you have the option of using unstructured mesh systems when you construct the algebraic equation system based on a volume integral of the original equation here on an unstructured mesh. That's quite okay. That's not something we can do with finite difference, of course. We have some other dirty trick which you should be aware of. And the one that they recommended in the text you have been given, that was not simple, it was called simple C. So you have a trick. Let's remove this one. Don't need this. You rewrite this equation here. And you could do it as follows. If you subtract sort of the sum of the coefficients on both sides, you can have it on this form. You will then have a p minus the sum of the neighbor coefficients, like that, multiplied with him, equals. Then on the other side, you will now have the sum of the neighbor coefficients, neighbor, multiplied with, and now a velocity difference, u neighbor minus the center point velocity. And then the same here, plus something delta p. Now you do the same dirty trick. You say this one is 0. Put a 0. Wow. Which is wrong, of course. But it's not so wrong as what we did down here. This was very wrong. This at least is going to be closer than 0. You have a difference in velocity here. So not so bad. So that actually, this simple trick speeds up convergence quite a lot. So this version of this equation here is what you called simple C. That's the only trick. And then, as I said, you have plenty of other tricks. I won't go into them. Simpler, simplex. I don't recall all the names even. Way too many. Any questions to these? You have some other dirty tricks as well, but I don't think I'll go through them. You can do a lot when you are manipulating with the momentum equation. Do some semi tricks. I mean, you have to cheat here anyway, so yes, you can still here. I think they normally use the density from the previous time step instead of the new one, if necessary. They take the continuity equation, which then should be 0. And then you can add the continuity equation on one side here. That's allowed. You just add 0, but it can still help the convergence rate. So yes, it's possible to do a lot of tricks to speed up the process. But that will be sort of code dependent, what people prefer to do or not to do. Okay, then I don't think I will bother you with anything else when it comes to unstructured mesh systems with finite volume. So I will stop it here with that. What I would like to show you before we end just so that the finite difference don't feel totally left out. I mean, using unstructured mesh systems is very convenient when you have a nasty geometry. But why can't we use unstructured mesh systems and finite difference? Normally it's not done, but yes, it's possible. It's possible. Just as an example, I wanted to show you finite difference. This is not going to be on any exam, so just have a look. Finite difference using unstructured mesh. When we create finite differences, we use Taylor expansions. Now we are going to have two-dimensional unstructured mesh, meaning we're going to need Taylor series, but I'm going to need him in 2 dimensions. And Taylor series in 2 dimensions, what do they look like? Well, you have an unknown function, say f, and you have given him a position a, b, and then we sort of change the position here with a small h, and the b position we change with a small k, something like that, equals, and then Taylor says, okay, this is equal to the value you have in sort of the center point, if you like, and then you will have plus, and then you will have a first order term, which now will look something like this. You will have the delta, say that one is in the x direction, then you're going to need the x derivative of the function, and then for y direction we had the distance k, fy, and this has to be then evaluated in the point AB, of course. And then you continue, second order term, 1 over 2 faculty, and then you will have something like this, h square, f double derivative, and then something new. Now you will have mixed derivatives, 2 times f x y. So derivative with respect to x and derivative with respect to y, plus k square f y y. Again, point A, B. And then you can continue for completeness if you want to have the general recipe, 1 over n faculty. You will then have an operator here, h d dx plus k d dy to the power of n, and then operating on your function f at the point A, B. So you see, extending Taylor to more than second term here is going to get really messy, more and more messy, of course. But it's possible. So yes, you can do this now and say you have an equation as an example. You just use a Laplace here for simplicity. And Laplace says then that the double derivative of f then reads fxx plus fyy should be 0. Okay, that should be fairly easy. And then what we are going to do, well, we take a Taylor expansion now in 2D. Taylor around, say, a single point x0, y0, and then Also I say f in this point. For simplicity, now I call him f0. Then find a neighbor point in either direction. Now you can play around going a distance both in x and y direction. So you can take any point around this center point 0, finding f number 1. What will he be? Well, he will then first be the center point, f0. And then we are going to need, if you go in the x direction, delta x1 fx. If you go in the y direction, you will have an fy. And then we are going to need some of these second order terms as well. Here we will now have, what will it be? Delta x1 squared half double and so on. Here it was delta x1, delta y1, not halved, no, just like that, fxy, the cross derivative. And then finally delta y1 square half fyy. Plus even higher order terms, third order terms. So here I have my center point, x0, y0, point number 1, and then somewhere up here you will have, oh sorry, this was 0, and this is then f1, x1, y1. Then yes, you can create an equation here. Okay, so now we say as follows. I want to find the unknowns here. And what is my unknown? Well, actually I want to find the solution in this center point. So this one, that's an unknown. I don't know him. Also in the center point, I don't know the derivative in either direction. Not to mention the double derivative, I don't know that one either. And this cross derivative, no idea. But finally the last one, this one, I cheat. Or not cheat. Here comes the equation. I have this one. Okay, so I substitute this one, that's minus f double derivative with respect to x. Okay, so that means I have 1, 2, 3, 4, 5 unknowns. Of course, then saying or implicit, we have a number for f1, so he's sort of given. But then that's one equation with 5 unknown. Okay. Then we need point number 2, we need point number 3, and we need a point 4, and you need a point 5. And that's all you need. Then you have an equation system, 5 equations, 5 unknowns. So you can then solve it, just saying that, I mean, you have the same equation system here, f2 equals, f3 equals, down to f5. But these will be the same in all the equations. The derivatives, remember, all of the derivatives are taking in the center point. So now it will represent 5 equations with 5 unknowns. So you just look at these as the unknown as well. Of course, in general, you will not be interested in them. You are interested in the f at that location only. But sort of as an additional benefit, yes, you can calculate the derivatives there as well if you want. It's not the best method, but actually it works. You just have to be careful when you construct the mesh, sort of a little bit random, but for one unknown you should have the neighboring points surrounding him, not just take 5 points to the left, for instance. That will be bad. So to get it more stable, keep your unstructured mesh systems, a little bit not structured, but a little bit regular at least. Also, be careful to use a random generator, for instance, if the distance here becomes very, very small. Also, then you will be in trouble. The equation system then will be quite rapidly non-singular and it will explode. But I tested this method actually and it works fairly okay. But you are limited then to very simple equation systems. Trying to do something like this with the full Navier-Stokes, thank you very much. I have no idea how that can be done. But this, more or less, just an example, a possibility here to think outside the box, think differently. Yeah, it might work. And here, yes, this works very nice indeed. Just totally random points all over the place and solve it using finite difference. Yes, we can do that. That's not illegal, but I don't think anybody is using this. I mean, I thought actually out this method myself, and I was very proud then. I thought I had found something very smart. And I showed this to one of my old professors, and he said, oh, by all means, this was the first thing they tried. So then I didn't feel so smart anymore. So it's a well-known concept. But it was rather fun, actually, to see that it worked. Okay, that's sort of beyond our topic, just for fun. Any questions from you? No? Then we stop with finite volume. We're only left with turbulence, and that should be done during next week. That's all, shouldn't take too long. Then the week thereafter, those of you who are interested can then show up and we will start playing around with open foam. And that will be sort of a crash course, meaning you have never touched open foam. If you have, then you don't have to come, at least not the first time. You can have a peek at the video instead. Well, should we take videos? Nah. That doesn't really make sense. You don't learn anything by looking at a video. If you want to do it, show up. But bring your laptop. Also, check that your laptop can be bootable from an external USB. That means you have to enter the BIOS into your machine and tell him that the first thing he should try is to find an operative system on a USB. Second, he can try his own internal hard drive, that's okay. But that can be a little bit messy on some computers. So have a look into the Google on your machine's exact model, how to access BIOS, how to tell the machine to boot from an USB instead of your internal hard drive. Because what I'm going to give you is then a memory stick with Linux and OpenFOAM. So you boot on the memory pin and then you don't mess up your own internal hard drive. If you have Linux already, then it's no big deal. Then you can install OpenFOAM directly. Shouldn't take too long. So that's an option. Anybody here uses Linux? Ah, you have some, yeah. Do you have OpenFOAM already, or yeah? And you have as well? And you also? Yeah, okay, no problem. But if you want to install OpenFOAM, just don't take the latest version. It depends on which version of Linux you are actually having on the machine, so they has to correspond. So check openfoam.org which version then is allowed on your Linux version. But again, that will then be not next week, but the week thereafter. We are finished with the lectures next week. Okay, yeah, I think yeah, there should be plenty of time to cover. It's only turbulence left. Yeah.
And which version are you using?
I'm using the latest 4.0, I think. Or yeah, maybe I can get time to find 4.1. Yeah. Other questions? then we stop here.